Thank you. So the simulated quantum annealing in the title is going to refer to a classical Markov chain Monte Carlo algorithm, and we're going to prove some new results on the convergence of this algorithm for a particular class of instances that we think have some implications for whether quantum annealing on true quantum computers can give us advantages in optimization. So the general topic is, the marriage of optimization and physics. So we're talking about combinatorial optimization, minimizing some real valued function on the domain of n-bit strings. And we're going to take some inspiration from physics. We're going to take advantage of dynamics in physical systems that drive them to low energy states. So this might be cooling in an environment, or it might be something, more interesting like sugar molecules that are too concentrated and want to climb out to form crystals. So of course the grandfather of this connection is classical simulated annealing, which is a local search algorithm that can be viewed as a Markov chain Monte Carlo simulation of the process of thermal cooling, where you're trying to sample some Gibbs distribution, where your energy function is given by the function f that you're trying to optimize, and you're sampling this distribution at some range of temperatures to kind of mimic the idea that you start at a high temperature and cool down to a low one, where you're hopefully likely to be in a low energy state. And so the question is, can quantum dynamics inspire faster optimization methods? Okay, well, the intuition, now this is very, very high level, quantum dynamics might allow for tunneling through high barriers in the energy landscape, right? We know that simulated annealing has trouble climbing high barriers because this is like hill climbing. You have several unlikely steps need to be taken in a row to climb over this hill, whereas somehow the uncertainty that's present, this sort of spread out nature of the probabilistic states in quantum mechanics, can allow it to maybe sneak through this kind of barrier and tunnel. Well, okay, so can we establish this intuition a little better? Well, we have some empirics now in 2016, so there's no useful speed up yet, but this company D-Wave that I'm sure many of you have heard of is trying to make these devices. So they have a noisy quantum annealer with about 1,000 qubits, and it's actually becoming competitive with modern single-core CPUs. Now, in terms of theory, it was proven maybe about 15 years ago that quantum annealing on quantum hardware can be exponentially faster than classical simulated annealing, or indeed any local search algorithm that resembles classical simulated annealing for particular cost functions, which we'll discuss more because those are the cost functions we're going to be concentrating on. But first I'll give this kind of overview of quantum annealing that assumes you don't necessarily have any quantum background. So we're going to have, we have our function f on this domain of bit strings, and just by convention I'm going to say that it takes these negative bounded values. So now I'm going to construct this diagonal matrix that just has the values of f along the diagonal. And then to describe the off-diagonal part, think of the n-dimensional Boolean hypercube and the negative of its adjacency matrix, and now define this weighted combination of that minus the adjacency matrix of the hypercube and this diagonal matrix that I've defined. Okay? And well, actually, let's back up and say this matrix has all non-positive entries, and so it kind of makes sense to talk about the Perron eigenvector, the principal eigenvector, which in this case, because it's all non-positive entries, will be the eigenvector corresponding to the least eigenvalue. Okay, so list the components of this eigenvector, and it's going to be unique as long as s is strictly less than 1, because this matrix is irreducible. Okay, so by the way, the eigenvalues correspond to energies in physics. So I'm going to call this the lowest energy sometimes, but it's really the lowest eigenvalue of this matrix, which depends on s. And now we're going to think about this distribution, which is proportional to the squares of the components of this eigenvector. Okay, and now where the quantum black magic comes in is that on a quantum computer, mu s can be approximately sampled in time that scales polynomially in n, and the inverse of this delta, where delta is now the minimum gap that you encounter sort of along the way to that point s. So there's a temporal aspect to this, which is how you actually implement it, which is you start at s equals 0, so you're entirely, so you have a very simple distribution, right? So the least eigenvalue in that, least eigenvector in that case is the uniform distribution on the bit strings. And then you're going to slowly change s until s approaches 1, And at that point, if you're in the least eigenvector when s equals 1, that's going to be the minimum of the function f, right? So, and as you slope E sub 1, sorry, this is refers to the spectral gap, so it is the next largest eigenvalue. And so indeed, so this quantity is the spectral gap that you encounter on the way as s goes from 0 to 1. And as long as this is at least as large as 1 over some polynomial in n, you'll get an overall polynomial time algorithm for sampling this distribution. Okay, so how was this exponential separation between quantum annealing and classical simulated annealing shown about 15 years ago? Well, we're going to define what looks like a very simple toy model. So it's we call it the spike cost function. It's a bit symmetric cost function with this large energy barrier that is designed to create a local minimum. So so this is the point n over 2, where your Hamming weight is n over 2. So the domain of this is bit strings. And we're going to imagine that simulated annealing or whatever optimization algorithm doesn't know about the symmetry of this problem. Okay, so initially you're at very, very high temperature, and you're likely to have your bit string distributed. It's going to be a binomial distribution around n over 2. And as you cool down the temperature, your simulated annealing walker is going to walk along here until it reaches this local minimum, at which point this barrier, so b and a here are constants independent of n. So this barrier is actually polynomial in height and width. And so even if you augment your simulated annealing algorithm with it can take maybe flip constant number of bits at once, that still won't be enough, right? You'll sit here and you'll say, well, this is just no man's land, and I'm never going to cross this barrier to find the true global minimum here. So indeed, it takes at least 2 to the n a time to solve with simulated annealing or any local search algorithm like SA. But it was actually proven by Reichard in a stock paper that quantum annealing succeeds in linear time when a plus b is less than a half. And just to give a little intuition about that, so when s equals 0, you have this binomial distribution, this uniform distribution on the bit strings, and it has some width that is going to be like square root of n. And so basically, when a plus b is less than a half, this quantum wave function, if you like, kind of slides on down, and somehow it doesn't even see the spike. And what I mean is you can use the variational principle to compare the system with and without this spike barrier term, and you find that the increase in the ground state energy goes to 0 as n goes to infinity when you're in this range of parameters. So indeed, this is just like so as far as quantum mechanics is concerned, adding the spike is just like not having the spike at all. And so it just doesn't see the spike at all, and it's kind of natural to use this comparison approach. Okay, so maybe this sounds really good, but maybe some of you who also work on things like spectral graph theory say, hey, this whole setup looks familiar and it looks kind of classical. So that's where I'm going to introduce this topic. So quantum annealing Hamiltonians have this property that we call stochastic. So stochastic Hamiltonians have non-positive entries, so they can essentially be just shifted and scaled to substochastic matrices, right? So our quantum annealing Hamiltonian, this matrix I defined, has this property. Now, since H is essentially a substochastic matrix, it does not define a random walk on the space of bit strings, right? We have this condition about a large spectral gap. So if we had a random walk with a large spectral gap, well, you wouldn't need quantum mechanics. You wouldn't need this interpolating the path. You would just go straight to the very end where you have a large gap, and you would run the random walk. But because it's substochastic, your random walk would just lose probability if you tried to do that. That algorithm goes nowhere. So the big open question is, can quantum annealing be classically simulated in polynomial time? For example, in complete generality. So more specifically, if we assume the minimum gap is some 1 over poly n, does this imply a polytime classical algorithm for sampling from the distribution at the end of the process? And nothing we know rules this out. Okay, so some additional results that kind of convince us that that something like this might be possible. Well, so deciding the ground state energy of a local Hamiltonian is complete for the natural quantum analog of NP, so it's QMA complete. But if you restrict the Hamiltonian to be stochastic, as the Hamiltonians in quantum annealing are, then it is actually in the class AM. So that's a big difference. And also, it was shown that quantum annealing with unfrustrated stochastic Hamiltonians can be classically simulated in polynomial time. But this condition of being unfrustrated is actually, it's a little natural from a physical point of view. For example, like a ferromagnet where spins all want to align are not frustrated. But from an optimization point of view, it's highly restrictive and essentially corresponds to a trivial cost function, at least in the model that I'm talking about to you guys today. So this problem is pretty much wide open. And okay, so it's wide open, and so we need some new techniques to solve it. And the technique that I've kind of focused in on in my research is something called simulated quantum annealing. So the idea in simulated quantum annealing, it's actually based on Feynman's path integral representation of quantum systems. And the idea is that we can obtain samples from this distribution mu by sampling paths that the system traverses through its state space. Okay, so this is what the stationary distribution will look like, except now our state space are these length L sequences where each element of the sequence is an n-bit string, right? So I've just kind of drawn an example here. You have the n bits and then just several more n-bit strings that kind of represent the future, if you like, of that particle. So again, our original state space was just this guy here, but instead of sampling points, we're now going to sample paths through this state space. And indeed, the distribution mu will just be the marginal on any one of these slices. On any one of these slices, it's actually going to be symmetric in that sense. So just to give you a rough idea of what this, how this stationary distribution behaves, well, it penalizes configurations for the proportion of time that they spend on bit strings with high values of f. So essentially, the stationary weight goes down exponentially in the average value of f if you averaged through all of the strings in the path. And it also goes down exponentially in the total number of jumps along the path, right? So you have this competition between sort of, if you like, energy and entropy, where you want to take some jumps because there's combinatorial many ways for that to happen, but you don't want to take too many jumps because then that will lower your stationary weight by too much. And so this method actually predates the idea of quantum annealing, and it's been used in practice by physicists for over 40 years. But the convergence of the chain is difficult to rigorously analyze. In fact, there are very few cases where this kind of Markov chain has been analyzed. And the use of this specifically for simulated quantum annealing, as opposed to like simulating materials in physics, goes back about 20 years. So it's, again, widely known to be effective in practice, but we have very few proofs that tell us how it should behave. So our result is that simulated quantum annealing for the spike system converges in polynomial time when a plus b is less than a half. So specifically, it equilibrates and finds the minimum of the spike cost function when these parameters are in this range. So you have the polynomial height and polynomial width of the barrier term, but somehow this simulated quantum annealing can still pass through the barrier. Okay, so just to write down some explicit runtime bounds we give, well, we consider two versions. So you have some stationary distribution, and anytime you have a stationary distribution with just this normalizing constant here, you think of doing like a metropolis algorithm. That's the Markov chain I'm talking about, or Glauber dynamics. So indeed, you could have the single site metropolis updates where you just pick one spin and propose to flip it, and we get some runtime bound for that. And then we analyze these non-local cluster updates that everyone uses in practice. Well, they look non-local, but remember, our original domain of bit strings, right, these are the bits. So you're really just flipping one bit, but you're flipping it its entire past and future, which in physics is called its world line. So, and these are like a generalized form of heat bath updates, which means you pick one of these world lines at random, and then you say, okay, well, erase everything in there and resample it conditioned on all of the other spins being the same. And one more thing, if you want to think about this stationary distribution in terms of bonds, you know, like the interaction edges, well, the Hamming weight is a non-local property on the n-bit strings, so you have almost complete connectivity in this direction, and you have actually ferromagnetic bonds in this direction. Neighboring spins want to align, but with some probability they can disagree. Okay, so now let's look at this results from, say, a numerical simulation just to get some idea for why this dynamics is challenging to analyze. So So essentially, this looks like a string with some amount of tension in it. So at s equals 0, when you have the uniform distribution on bit strings, this thing just looks like a Brownian motion, right? So it has some deviation, and maybe I didn't say this on the other slide, but it actually has periodic boundary conditions on the path. Now, each of these, and this is the L direction, just like before, and this is the n bits direction, right? So this is centered around n over 2, and this is sort of this length of this fictitious direction. And by the way, this fictitious direction is actually a discretization of time that you have to choose fine enough to avoid error, but it's just, so L is basically some polynomial in n to get whatever error scaling you want. As we tune up this S, right, so all these guys are jiggling around. Each of them wants to go to lower energy states, but they can't get too far away from their neighbors, right? Something like this costs you a big energy penalty. So there's a lot of competition between these guys jiggling around. But up here, they don't feel the spike yet. And then they get down here, they start to kind of bunch up, because actually crossing the spike, which is at n over 4, is maybe a little harder than just moving freely like they often do. Okay, so then you reach some critical value where some have passed through the spike, but others have not, right? So you're kind of sitting on it. And then once you pass through it completely, well, you're pretty much home free. So, if you're used to analyzing Markov chains, you can think that this string-like object is going to be kind of hard to analyze. So what are the ideas of our proof? Well, we compare simulated quantum annealing Markov chain with and without the spike term, sort of paralleling what was done in the quantum proof. So for the worst case configurations, the spike distribution may be very different from the spikeless distribution. So if the configuration spends a lot of time on the spike, it'll have a much lower weight when the spike barrier term is present. But using expectation values from the quantum system, we can show that for typical configurations, these two distributions are actually quite similar. Okay, and by the way, so we kind of actually heard a bit about this in the last talk. A lot of the standard mixing techniques are designed for worst case pair of configurations, and that's why we couldn't just apply a standard comparison technique. So what we do is we use canonical paths for the spikeless system to construct canonical paths, and again, these are canonical paths in the sense of Jerram-Sinclair, and how you Jerram-Sinclair, and how you analyze oftentimes these complicated these Markov chains with complicated weights on their stationary distribution. So we use canonical paths for the system without the spike to construct canonical paths for the spike system, but only within a typical subset, and we're able to show that leaks outside of this subset are rare. So this is actually something slightly new in the analysis of Markov chains, and what we really get is quasi-equilibration of the simulated quantum annealing into the subset of the state space, and we actually use the adiabatic path to guarantee warm starts that keep us in this subset. So just to say a little bit more about this most paths comparison, we call it. So again, the idea is that typical paths have similar stationary weight. So you have this. So you have your overall state space omega, and you're going to divide it into omega g, omega good points, and then you have this omega b, the bad points, which are like punctures in your space. And for the easy to analyze Markov chain in your comparison method, you have some set of canonical paths already, okay? And you know it's congestion. And so what you want to do is you want to port those paths over to your difficult to analyze system. But what happens is, so many of the paths won't pass through a hole at all. But of course, some of them will. But when that happens, you'll always sort of just be able to do something like this. You'll just be able to go to some intermediate point and take a different path. So we state this in our paper as a general theorem. Of course, there are some conditions on what the total weight of these punctures, which is like 1 over some polynomial, maybe the degree of the vertices in the Markov chain, and so on, but it's not very restrictive. I think you could actually conceivably use this for other problems where you had an easy to analyze chain and the hard to analyze chain was similar within typical configurations. And so ultimately what we get is that they have the same congestion within this subset. So now just kind of wrapping up. So we've shown that simulated quantum annealing can inherit some of the quantum advantages in quantum annealing. And so this actually provides the first proof that this sampling of paths can be exponentially faster for a particular class of optimization problems than standard simulated annealing. So now one of the things that was nice about this is that we use the adiabatic path in an essential way. So normally when you have a Markov chain, it's really designed to forget where it came from. But we know that in quantum annealing that the path must be essential, right? Because if all that mattered was the gap at the value of S that you're at, you would just kind of jump to the end. Jump to the end where your matrix is diagonal, and you would have a large gap. So we know that the adiabatic path is essential. So that means something like this has to come into the analysis. You can't just have rapid mixing at each value of S. Now, maybe something for people in this room to think about, is this local search on the space of bit string paths truly a useful alternative? Okay, independent of its connection to simulating physics. And finally, is an efficient classical simulation of stochastic quantum annealing possible in general? I would love if anyone has any ideas, shoot me an email. We could collaborate. All right, thanks for your attention. Absolutely. So everything applies, I mean, except our analysis. So the algorithm still exists, it still converges, but you don't have a guarantee on its convergence. But you know, if you care about sort of the numerics that people have done to back up this heuristic, it seems that it works as well as the quantum system does. And of course, you can't solve these things in polynomial time anyway. Yeah. Okay. Yes. Yeah. Exactly. It was probably either Matthias Troyer or Helmut Katzgraber. Oh, sure. This. Yes, I am. So in other words, do these kind of tall but narrow barriers occur in realistic problems that people care about? Well, that's the central question to whether quantum annealing is going to be useful or not. So you have many groups that are studying this. Google says, for example, that they think integer partitioning will be a problem that has this behavior. So people are very much looking at that question. But as you can see from my talk, sort of the state of theory is far behind the state of heuristics currently. Yes, it's exactly relevant. And so what they do is you can use this idea to contrive endless examples, right? And you can also generate a lot of random ones and select the ones that have this feature. But we're still essentially looking for the class where quantum annealing would be most useful. Some class of problems where even just typical random instances have this behavior and you get a large speed up. Yeah. Okay, fair enough.